We're going to start this topic by looking at the law of conservation of energy. It's a basic law of physics and applies throughout the universe. And you may have heard it stated that energy cannot be created or destroyed. That's true. The total amount of energy in any given system always remains conserved. It remains constant. Now, the energy in one object might change, and the energy in another object might change, or the energy in one store or form or type might change, but it is always transferred into another form or store, meaning that the total remains constant. It's a bit like the conservation of momentum. The momentum of individual objects might change, but the total remains the same, and that's the same with energy. So here's a statement of the law of conservation of energy, which we're going to consider. The law of conservation of energy states that, in particular, the total amount of energy in a closed system remains constant. Now, this bit about the closed system means no energy can escape or come into the system, so no energy going in or out of the system. And a lot of our closed systems are approximations to that, because energy can leak and does leak, and we'll talk about that later. Like anything else to do with energy, this one is measured in joules with a capital J, and that's the unit, the standard unit, the SI unit of energy. Okay, so let's have a look at some of the stores, some of the types of energy that we can have. So a store is basically an amount of energy within an object or within a system, and there are different stores, different types of store. And here's a list of some of them. So chemical energy is a store that is stored within the bonds of a chemical, a molecule or whatever. And that can be released by breaking the bonds, but we'll talk about that later. So it's chemical energy stored in molecular bonds. For example, fuel. So fuel contains chemical energy, and when you burn the fuel, you break those bonds in the chemicals and you release that energy. Kinetic energy is another word for energy due to movement. So moving objects have kinetic energy, and as we'll see later, this depends both on the mass of the object and the velocity of the object. So obviously an example of that would be a moving car. Nice, easy, everyday example of a store of kinetic energy. Let's have another one which is completely different. The wind is a store of kinetic energy because it's moving. Gravitational energy is about height. So an object that is raised up against gravity has a store of gravitational potential energy. So a good example of that would be the moon, having a store of gravitational energy, quite a large store of gravitational energy, sometimes called GPE, this one, or sometimes just called potential energy. We're going to call it gravitational potential energy quite a lot. So the moon, or a bag on a high shelf, something like that, anything that has been raised upwards away from the earth, away from the ground. Elastic energy is anything that's stretched or compressed, so something that is not its normal length, effectively. So a stretched elastic band would be a good simple example of something that has a store of elastic energy. Thermal energy, obviously, it has to do with the microscopic movement of molecules. So in some ways, thermal energy is similar to kinetic energy, but on a microscopic level. But effectively, anything that's hot, and the hotter it is, the more thermal energy it has, or the bigger it is, the more molecules it has, the more thermal energy it has. So obviously a good example of that would be a fire or a hot cup of tea, something very close to my heart. Magnetic energy is due to the presence of certain molecules, or certain atoms rather, in magnetic materials. So magnetic materials and magnets in particular, sorry, I was going to write magnetic materials but changed my mind, I'm going to write magnets, have magnetic energy. Electrostatic energy comes from charges, so things like electrons and protons. You can charge objects up by adding electrons to them or taking away electrons from them. So, for example, a balloon that's been rubbed is an everyday good example of electrostatic energy. Or simply, the area around an electron will give you an amount of electrostatic energy. And then nuclear, that comes from the nucleus of atoms, and can be released when the nucleus is broken down, or a new one is formed. So nuclear energy, for example, nuclear fission is a process that releases nuclear energy. So there we go. So those are some stores of energy, different stores formed and stored in different objects depending on the context and the different type of energy. And then energy can be transferred from one store to another, excuse me, or from one object to another, and that can happen in different ways. Mechanically, by use of a force; electrically, by use of a potential difference or a voltage. That will transfer energy electrically via the flow of a current, usually, by heating, and by radiation, such as the transfer of energy via light and sound. So those four different types of transfer can transfer energy from one object to another, or from one type of store to another. Okay, so let's have a little think about the concept of that. So here is an analogy to that. I'm going to have two different reservoirs here, and they're going to be filled with water. And one of them is filled with water like that. Oh, sorry, that's not quite right. That line should go down there. One of them is filled with water to that level, and one of them is filled with the water to that level. And there's a pump. And the pump can pump in either direction. And this is a large store of energy, or large store of water, and this is a smaller store of energy. The pump represents the transfer of energy. So if you turn the pump on, some of the water will flow down here and along this pipe, and then up into this one. And the value of the volume of water in this second reservoir will increase, and the volume of water in the first reservoir will decrease. But in total, the same amount of water is there. So it's quite a simple analogy for an energy transfer. This would be a large store of energy over here, and then that could be transferred into another store of energy. So when one store of energy decreases, another one increases to keep the total amount the same. And that's the basic idea of the conservation of energy. So one of your jobs is to identify which stores of energy and changes in energy stores occur in different contexts. So here are a few. So a ball being thrown upwards or rolled up a slope. Now I'm sure you've done these sort of energy flow diagrams before, but let's have a look here. I'm going to focus on the useful energy where possible. So a ball being thrown upwards, so it's going upwards, and it's being thrown, or it's going to be rolled up a slope. So it's gaining height, and as it does so, it slows down. So initially the ball would have had a fair amount of kinetic energy as it was thrown, or as it began to roll, and that would then be transferred into a store of gravitational potential energy as it goes upwards. But the total amount of energy, when you add up the value of the kinetic and the value of the gravitation at all points along that journey, or along that path, the total will be constant. A cricket ball being stopped by a bat. Okay, so the cricket ball, again, as it's moving through the air towards the bat, it has quite a lot of kinetic energy. That is then completely transferred as it's stopped, and quite a lot of it is transferred into thermal energy, making a little hotspot on the surface of the bat, raising the temperature of both the ball and the bat because of the impact, and there'll be quite a bit of sound produced as well from the noise. So sound energy, which is an example of our radiant transfer. So technically we're looking at a transfer of energy through the sound, with a store of thermal energy produced. Okay, a car under constant acceleration. Well, the car is fueled I would imagine, by petrol or diesel. So let's take a combustion engine car. So that is a store of chemical energy in the fuel. And as it's speeding up, that energy is then converted into kinetic energy. There will be other energy forms, other energy stores that also increase, such as thermal energy and sound energy, or a transfer of sound energy, and also some electrical energy produced by the car. But that's the main one. That's the useful one in general, chemical to kinetic. And then a car slowing down. So based on the action of its brakes, we have quite a lot of kinetic energy in the moving car, and that is then transferred through friction. And this is going to be a common theme. Friction produces heat. The action of that mechanical transfer due to the force of friction produces quite a lot of thermal energy. And actually cars' brakes can get quite hot when they've done a lot of braking. And then an electric kettle of water being heated. So here we start off with electrical energy, and that is then transferred into thermal energy as well. So that's the two balance of the two stores there. The store of electrical energy goes down as the store of thermal energy increases. Okay, but not all of it goes to where we want. And in any energy transfer that occurs between one store and another via any of those transfer methods, in almost every single case, part of that original energy store is wasted. Some of it, sometimes most of it, gets transferred into something that we actually want, but a lot of it, in some cases, the majority will be wasted. And usually with a mechanical transfer, that becomes wasteful when it causes a rise in temperature of the system. So when the temperature goes up, that then dissipates that energy into the surroundings. And that is no longer useful. So the energy that's transferred into the surroundings, usually by heat or by a radiant transfer from a hotter object, is no longer useful and cannot be used again. So energy disappears from the system forever, and effectively just heats up the surroundings. We don't want that to happen usually. Energy is expensive and valuable, and so we want to try and limit the unwanted energy transfers. And there are two main ways to limit unwanted energy transfers. The first way is to use insulation, like putting on a jumper. That's an example of using insulation to limit or reduce an unwanted energy transfer. And insulation is usually used in situations where a mechanical transfer through friction is not happening. And the other way is through lubrication. So, for example, engines and moving parts in gearboxes, etc. A way to stop them getting hot, to reduce that unwanted energy transfer to heat, is by lubricating them, by oiling them, by putting in some sort of fluid that helps reduce the frictional force and therefore the unwanted energy transfer.